Welcome back. In this session, we will discuss scientific method part 1. When we recall the evolution of science, we come to know that the scientists of ancient and medieval times, with the exception of few such as Archimedes and Hippocrates, adopted philosophical approach in finding solutions to their scientific problems. The adoption of pure experimental method in scientific investigation began only in 17th century. Till that time, philosophical enquiries and scientist enquiries shaded each other. This was so because all the scientists were philosophers and most of the philosophers were scientists. The method of inquiry adopted by the philosophers were speculative than scientific. In investigations, while the philosopher speculates on the entire field, while the scientist remains close to reality and does not attempt to pose impossible problems which he cannot answer. Science contains statements based on facts, demonstrable, provable and verifiable by experiments. In solving problems, scientists use a combination of reasoning and experimentation, but philosophers use only reasoning. The scientific method has philosophic background. Scientific method, meaning and the steps involved. Scientific method means the method or procedure adopted by scientists in their investigation of natural phenomena. The way in which scientific generalizations are arrived at and made use of. The scientists mostly arise out of the instinct of wonder and curiosity. They aim at bringing an event or a phenomenon into an intelligent system into which it fits. Basically, scientific method is a problem solving method. Scientific method involves reflective thinking, reasoning and results from the achievement of certain abilities, skills and attitudes. A problem may arise in connection with the desire to meet the practical need. For example, the discovery of Bacillus anthracis. Dr. Ronald Ross was an army doctor in India. He was sorry for many sufferers from malaria that he saw every day and determined to do something to help them. During some local leave, he stayed in a rest house with another officer. Ross used a mosquito net, the other officer did not. Ross did not get malaria and the other officer did. Ross noted that this way was easy to explain that the bites of mosquito carry malaria. This was a guess or hypothesis. Ross decided to test this guess that mosquitoes carried malaria. He therefore caught mosquitoes and made them to bite people with and without malaria. He studied their blood, he studied about mosquitoes and many other things. On this way he had many failures, but at the end of 5 years he found that exactly how a certain kind of mosquitoes carried malaria. Later on he was able to tell the people how to control malaria, and later his ideas worked in stopping malaria in Freetown, South Africa. The story of Ross and malaria shows how a clever, eager and determined man recognized a problem and looked for an answer to it. The first step was the observation. He was bitten by mosquitoes and got malaria. I was not bitten and did not get malaria. The next step was the guess. Mosquitoes carry malaria. The third step was the test by experiments, which took 5 years, and the experiments proved that the guess was correct. The 3 steps in this, which works all in science, was observation, guess and experiments. Definition and nature of scientific method. Fitzpatrick defined science as a cumulative and endless series of empirical observations which results in the formation of concepts and theories, with both concepts and theories being subject to modification in the light of further empirical observations. Science is both a body of knowledge and a process of acquiring and refining knowledge. Lundeberg defines scientific method consists of systematic observation, classification and interpretation of data. Many teachers accept scientific method as an important objective of science teaching, and yet nothing was provided for the conceptualization in scientific method because teachers commonly tend to assume that scientific method is just an outcome of science teaching, and therefore no deliberate effort was needed to train this method. Scientific method involves reflective thinking, reasoning and results from the achievement of certain abilities, skills and attitudes. Present evidence indicate that it needs a continuous training and is the outgrowth of a day-to-day work with problems concerning the students in an atmosphere of careful and persistent investigation. Steps involved in scientific method. Scientists follow a rigid and pre-planned procedure in attacking and solving their problems. They use different ways and means of solving their problems, but one can notice that certain common elements or phrases of procedure in all types of scientific investigations, and scientific method refers to these common phrases of procedure in the solution of scientific problems. So, a complete act of scientific method can be analyzed through the following steps. First, sensing the problem. Next, defining the problem. Third, analyzing the problem. Next, collecting the data. Next, interpreting the data. Formulation of tentative solutions or hypothesis. Selecting and testing the most likely hypothesis. Drawing conclusions and making generalizations. Application of generalization to new situation. First, sensing the problem. A problem is a felt difficulty. It is the gap between what we have and what we want. It is a situation in which one does not know which way to proceed. In the learning situation, the learners quite often feel the need for asking some questions. The teacher may also put such questions which require reflective thinking and reasoning on the part of his students, and this may become a problem for the students to solve. The problem set should fit in with the curriculum and should appeal to the majority of students in the class, so that it will foster group work which makes for greater reflective thinking. Defining the problem. A felt problem can be solved only by grasping the problem meaningfully. This is possible only if it is defined in clear, definite and concise language. There will be some key words in the statement of the problem which may help in the better understanding of the problem. The teacher should help the students in stating the problem. The student may be asked to write down the statement of the problem in the light of above criteria and then read it in the class for criticism and discussion. Analyzing the problem. The key words and phrases in the problem which furnish clue to the further study of the problem. The key words help in finding out the required information. It is, however, important that the student should know the meaning of all the keywords and understand the whole problem, and when the students have grasped the problem, half of the work are done. Collecting the data. Analysis of the problem would help to collect the relevant data or evidences bearing upon the problem. The teacher suggests references to the problem. The students consult the references and collect evidence bearing upon their problem. It is a good opportunity for the teacher to guide the students in developing a variety of skills and techniques. Information can be gathered by reading books, making field trips, performing experiments and discussing with the experts. The students should be given practice in locating information and to devise means to obtain it. Interpreting the data. After collecting data, these have to be critically examined with respect to relevance, appropriateness, clarity, etc. Superfluous items may be discarded and incomplete ones are refined or completed. It is an important and at the same time a difficult step, for it involves reflective thinking and is complex of skills and abilities. Students require lot of practice in interpreting the data. It is wise to break the data into simpler ones and interpret and later on consolidate meaningfully so that the interpretation is for the whole data. Formulation of tentative solutions or hypothesis. Having interpreted and organized the data, students may be asked to write down inferences based on the given evidence and to propose ways of testing out these inferences. This leads to large number of hypotheses. Selecting and testing most likely hypothesis. Selecting most likely hypothesis out of number of hypotheses requires special skill and involves analyzing, selecting and interpreting the relevant data, judging pertinence or significance of the data for immediate problem. The students can select most tenable hypothesis by rejecting others through discussions and experimentations. The selected hypothesis is again tested experimentally to find out its truth, drawing conclusions and making generalization. The tested hypothesis is the conclusion to be reached at. However, such classroom situations may be provided as may help in drawing conclusion. The generalization can be made by arranging a set of experiments which also show the same conclusion already reached at. Application of generalizations to new situations. The student should apply the generalization to their daily life. This will bridge the gap between the classroom situation and real life situation. As it is important to start the cycle of reflective thinking with a problem which is interesting and useful to the students, so it is important to close the cycle with application of generalization to new situations. So it is quite clear from the above discussion that scientific method involves a definite set of procedure for attacking the problem, finding out its solution inductively, and lastly testing the adequacy of generalization by deductive approach. Some elements of scientific method. Characteristic features of scientific method. Scientific method is only the expansion of the thought process. The characteristic features of scientific method are the following. First, a problematic situation that finds no ready solution is the starting point of the scientific method. Scientific problems are usually concerned with the cause-effect relations and lead to the discovery of new generalization or application of non-generalization to explain non-facts. Observation, measurement, critical examination of likeness and differences and abstractions required for the definition of the problem. Searching reflections consisting of analysis, synthesis and use of methods of reasoning lead to suggestions of probable solutions or hypotheses. The implication of each hypothesis are reasoned out and tested by comparison with observed facts and by further observation and experiments. If the deviations from the hypothesis do not agree with the observed facts, they are rejected, and the process is repeated till the suggestion which agree perfectly with the observed fact is obtained. The conclusions are subjected to repeated test. Hence, scientific conclusions possess a higher degree of certainty than those in other fields. But scientists keep their generalizations in plastic state and they are always ready to amend them in the light of new experiences. This is because scientific knowledge undergoes changes in the course of time. Some elements of scientific method. Scientific method primarily makes use of two types of reasoning in drawing inferences. They are induction and deduction. Induction is the process of arriving at some kind of order or regularity among the phenomenon observed. Deduction is the process of applying inductive conclusions, laws or regularities to the particular cases. Induction is from particular to general and deduction is from general to particular. Deduction. Greek philosophers Aristotle and his followers introduced the use of deductive reasoning, which one proceed from general to specific using prescribed rules of logic. A formula or definition is accepted by the individual as well established truth for interpreting specific problematic situation. Deductive reasoning works from the more general to more specific. It is top-down approach, beginning with thinking up a theory about your topic of interest, then narrow down that into more specific hypothesis that you can test. Narrow down even further when you collect observations to address the hypothesis. Ultimately, test the hypothesis with specific data and leads to confirmation. The deductive reasoning operates through a series of statements known as syllogisms containing the major premise, the minor premise and conclusion. For example, in a general case, all men are mortal is a major premise. Socrates is a man is a minor premise. So, Socrates is mortal is the conclusion. In science, metals conduct electricity is the major premise. Copper is a metal is a minor premise. So, copper conducts electricity is the conclusion. In deduction, if the premises are true, the conclusion is necessarily true. Hence, we must begin with true premises in order to arrive at true conclusions. Scientific inquiry cannot be conducted with deductive reasoning alone because it is not dealing with single phenomena. Deductive reasoning is very helpful in linking theory with practical observations. Next, induction. Francis Bacon was the advocate of this type of reasoning. He was of the view that thinkers should not enslave themselves by accepting premises handed down by authority as an absolute truth. He has emphasized that an investigator should establish general conclusion on the basis of facts gathered through observation. Inductive reasoning is moving down from specific observations to broader generalizations and theories. It is bottom up approach, beginning with the specific observations and measures, formulate tentative hypotheses that you explore and finally end up developing some general conclusions and theories. Inductive reasoning is the reverse process of deductive reasoning. For example, deductive reasoning: every mammal has lungs, all rabbits are mammals, therefore rabbit has lungs. In inductive reasoning, every rabbit that has ever been observed has lungs, therefore every rabbit has lungs. In deductive reasoning, premises must be known before the conclusions are reached, but in inductive reasoning, conclusions are reached by observing examples and generalizing from the whole classes. A perfect inductive reasoning can only be possible by observing all the observations of a phenomenon, and this is not possible. So, generally we rely on imperfect induction based on incomplete observation. Assumptions of inductive method: all inductive inferences are based on the following assumptions, but the theoretical proofs for these assumptions are not possible. First, the law of uniformity of nature. A phenomenon that has taken place under certain circumstances will repeat itself whenever the same circumstances occur. Law of causation: every phenomenon has a cause or a set of causes that is invariably connected with it. In other words, nothing takes place in this world by mere chance. Often it is difficult to find all the possible causes and to find conclusive reasons. In complex cases where there is a plurality of causes, it is difficult to decide which is the cause and which is the effect. In such a case, we try to establish the causal relation by adopting one of the following 5 methods of induction known as Mill's 5 canons of induction. Mill's 5 canons of induction. John Stuart Mill has given 5 different canons or principles of induction. They are the method of agreement, the method of difference, the join method, the method of residues, the method of concomitant variations. The method of agreement. The method of agreement states that if in every observed instance of a phenomenon only one circumstance is common, that circumstance is probably the cause or condition of that phenomenon. Symbolically, we have A, B, C, D, P, Q, R and S are the conditions of the phenomenon in the first case. Then B, C, E, F, Q, R, S, T are the conditions of the phenomenon in the second case. Now C, E, F, G, X, P, R, Y are the conditions of the phenomenon in the third case. Therefore, C, R may be the cause for the phenomenon. Example: when we compare different substances which exhibit the phenomenon of efflorescence on no other point of agreement, in all cases we find that substances contain water of crystallization and that there is no other common circumstance, we may legitimately conclude that presence of water of crystallization is the cause of efflorescence. Next, if dew is found deposited on a number of surfaces which are different in all respect except that they are all at lower temperature than the surrounding atmosphere, then Lower temperature may be the cause for the deposition of dews. The conclusion obtained by this method are not decisive unless a number of varied instances are considered and all other casual circumstances are eliminated. The method leads to absurd inferences. The method of agreement, though not foolproof, may with the proper caution be made use of for suggesting clue to be followed up by other methods. The method of difference. The method of difference states that whenever the elimination of a single circumstance is accompanied by the non-occurrence of a phenomenon, that circumstance is probably related to its causation. Symbolically, you have positive instance as ABCD PQRS and negative instance as ABC PQR. So, D and S are the cause of the phenomenon. Example: if a surface exposed to air is dry at the atmospheric temperature and it becomes wet on lowering its temperature, other conditions remaining unaltered, we might reasonably conclude that lowering of temperature is the cause of wetness. Next, a musical note is produced when the violin string vibrates, but when the vibrations are stopped, other conditions being the same, the note ceases to be produced. Hence, we infer that the vibrations of the string to be causally connected to their note. The method of difference is very largely used in experimental science. Each of our activities produce an effect, and when the effect is absent in the absence of the activity is considered as the cause of the effect. In this method, we compare two instances, one in which the phenomenon occurs and the other in which it does not. What is most important is that they should differ only in one relevant circumstance. The two instances may be two successive states of the same set of circumstances differing by only one antecedent and one consequent, or there might be two independent and separate instances, but it is rarely that we meet such instances in nature. Hence, this requirement should be arranged for experimentally taking care that no more than one circumstance is varied at a time. Under such conditions, the method of difference yields good results. The join method. Join method states that if in a group of cases in which phenomenon occurs, there is one and only one common circumstances, while in another group of cases in which the phenomenon does not occur, there is nothing in common except the absence of the above circumstance, then the phenomenon is causally related to the circumstance. Join method is the combination of method of agreement and method of difference. The suggestion of causation arrived by the method of agreement is strengthened by the method of difference. The application of this method leads to fairly valid conclusions. The method of residues. The method of residues states that if part of a complex phenomenon is not to be causally related to certain operating circumstances, the residual part of the phenomenon must be due to the rest of the relevant circumstances, may be known or unknown. The method suggests how we must obtain a complete knowledge of a complex phenomenon, part of which is already accounted by its non-causal relationship with certain circumstances. Obviously, the unexplained residual part of the phenomenon must be due to causes which may or may not be known to exist. The method does not necessarily help us to determine the cause of the residual phenomenon, but it limits the field of inquiry and make it easier to hit on a suitable hypothesis. Examples: the orbit of Uranus as observed by astronomers was found to be slightly different from the nature as calculated on the basis of the law of gravitation, even though the influence of all the non-planets had been taken into account. The residual deviation of orbit was therefore assumed to be due to the influence of some unknown planet. Finally, the calculations revealed the presence of planet Neptune. The interval between the successive eclipses of Jupiter's satellites was observed to be not quite uniform throughout the year. It was found to vary between two limits according as the Earth in its orbital motion moved towards or away from Jupiter. The residual difference in the observed periods led to the measurement of the velocity of light. Similarly, the residual density of atmospheric nitrogen in comparison with the pure chemical nitrogen led to the discovery of argon. The method of concomitant variations. The method of concomitant variations state that if two phenomena vary concomitantly while all other relevant circumstances remain unchanged, they must be causally related. Symbolically, we have A, B, C, D1, P, Q, R, S1 are the conditions of the phenomenon in the first case, and A, B, C, D2, P, Q, R, S2 are the conditions of the phenomenon in the second case. Then A, B, C, D3, P, Q, R, S3 are the conditions of the phenomenon in the third case. Then D, S is the cause of the phenomenon. The method implies that the quantitative variation of the antecedent produces a quantitative variation of the consequent. It is also helpful in establishing quantitative correlations between causally connected phenomena. This is the most important method employed in science. The validity of such quantitative laws will mainly depend on the degree of accuracy with which the varying phenomena are measured. It must also be remembered that these laws are applicable only within the limits between which the phenomenon have been varied experimentally. The concomitant variation may be of two types, direct or inverse. When the antecedent and the consequent increase or decrease together, it is said to be direct. When one of them increases as the other decreases, the variation is inverse. For example, the gravitation between two bodies varies directly with their masses and inversely with their distance from each other. Examples: first one, the change of volume of a gas is observed to be accompanied by a change of temperature as well as a change of pressure. To decide which of them is the cause or whether both of them are independent causes, it is not possible to eliminate either, but each of them must be kept constant and other varied. The observations thus made reveal that concomitant variation of pressure and volume and also of temperature and volume. Hence, we conclude that both pressure and temperature are causally related to volume. Next, it is found that the time of motion of a body and frictional forces encounters vary concomitantly. From this, we infer not only the causal relation between two elements, but also the quantitative law correlating them. Extending the quantitative law to the limiting case when friction is absolutely eliminated, which is impossible in practice, we may conclude that body would move incessantly in the absence of resisting forces. This is an idea that contained in Newton's first law of motion. The above method of induction suggested by Mill should not be considered as infallible. They cannot invariably suggest causal relations. Difficulty arises either when the same effects such as motion or heat may be produced by a plurality of causes, or when different effects remain mixed up in so far as they suggest general line of inquiry. Analogy. Scientific method makes use of analogy also in drawing inferences in scientific investigations. Analogy is the most primitive type of inference. Whenever we perceive a new object or an event, the first impulse of the mind is to compare and connect it with the nearly similar previous experience. When two objects or phenomenon are similar in some respect, we anticipate that they would be similar in some other points as well. The recognition of such analogy is helpful in understanding new experiences and suggesting causal relations. In fact, the first insight into the nature of an apparently new object or phenomenon is commonly obtained by analogy. In science, analogy has played an important role in the fields of discovery and explanation. The wave theory of sound was suggested by ripples on the surface of water, and the wave theory of light by the propagation of sound waves through air. The heliocentric theory of the solar system has its support from the analogy of the miniature planetary system of Jupiter and satellites. The conclusions drawn by analogical reasoning are much less reliable than those of induction, because no invariable connection is established between the antecedent and the consequent. The validity of conclusions drawn by analogy depends not as the number of points of similarity between the phenomena compared, but upon the depth of the resemblance between them. Very often, it may happen that the similarities are only apparent or superficial. In such cases, we are likely to mislead by analogy. The ability to assess the importance of similarities and differences can be acquired with the experience and knowledge. Hence, analogy should be handled with great precision. Analysis and synthesis. Analysis and synthesis are the real foundations of scientific method. Analysis means separating into parts and synthesis means putting together. Inference is possible only through the mental process of analysis and synthesis. In induction, we analyze the various facts into various components and synthesize them to formulate relationships. In deduction, we analyze general proposition and apply it to particular cases. Things and events of nature that form the materials of science are mostly complex in their conditions, and we have to analyze them into their constituent elements before we can discover any order. Progress in science depends on a very large extent on the ability to separate ideas that nature has closely combined into a unified whole. Analysis is facilitated by comparison of different objects or phenomenon which are similar in some respect. Human mind has got the innate tendency to note the similarities and differences. Having analyzed the phenomenon, we have to synthesize them into different ways by combining the common aspects. Thereby, we can develop class concepts and formulate definitions. By connecting different conditions, we can discover causal relations or law. Hypothesis, definition and nature. Hypothesis is a shrewd guess or inference that is formulated and professionally adopted to explain observed facts or conditions and to guide in further investigation. It is a plunge into the unknown. Hypothesis plays an important role in scientific investigation. Critical examination of the observed facts and purposeful reflection lead to suggestions of tentative solutions. These tentative suppositions are called hypotheses. Burnon's case defines a hypothesis is a statement temporarily accepted as a rule in the light of what is at the time known about a phenomenon and is employed as a basis for action in the search for new truth. When the hypothesis is fully established, it may take the form of facts, principles and theories. In scientific investigation, random search for a solution will not serve any purpose. It will only serve to turn up a multitude of facts. But if there is a working hypothesis, it will determine the particular line along with the investigation to develop. Hypothesis is the groundwork in which the whole investigation is built up. Sources of hypothesis. It is difficult to describe how hypothesis is formed. Analogy and simple methods of induction are helpful in forming hypotheses relating to causes that are perceptible to senses. Breadth of knowledge and the imaginative insight of the investigator are helpful in the formation of hypothesis. For this, the investigator should have a wide reading, familiarity with existing practices and first-hand contact with the pertinent data. Discussions, lecturing about the problem, drawing and constructing models relating to the problem will help in the formation of hypothesis. In general, it was aid that hypotheses occur to the mind that are prepared to interpret facts. For example, Newton's hypothesis relating to the pull of gravity on falling bodies, Kekule's hypothesis on dynamic structure of benzene, Robert Koch's hypothesis relating to the discovery of the cause of anthrax. Purpose of hypothesis. The following are the purpose of hypothesis. First, the hypothesis provide tentative explanation of the phenomena and facilitates the extension of knowledge in an area. The hypothesis provides the investigator with a relational statement that is testable directly in an investigation. The hypothesis provides direction to research. The hypothesis tells the investigator what to do and how to proceed. It helps to keep the investigator restricted in scope, preventing him from becoming too broad and unwieldy. The hypothesis provides a framework for reporting the conclusions of the investigation. Characteristics of good hypothesis. First, hypothesis should be clear and precise. If the hypothesis is not clear and precise, the inference drawn on its basis cannot be taken as reliable. Hypothesis should be capable of being tested. In a swamp of untestable hypotheses, many a time the research program has bogged down. Third, it should be self-consistent with the most known facts, and the conclusions derivable from it deductively must not contradict. Next, the hypothesis should state the relationship between the variables, if it happens to be a relational hypothesis. Next, hypothesis should be limited in scope and must be specific. A researcher must remember that narrower hypotheses are generally more testable. Hypothesis must be amenable to testing within the reasonable time. One should not use even an excellent hypothesis if the same cannot be tested in reasonable time, and one cannot spend lifetime collecting data to test it. Next, hypothesis must explain the facts that gave rise to the need for explanation. This means that by using the hypothesis plus other non-accepted generalizations, one should be able to deduce the original problem condition. Thus, hypothesis must actually explain what it claims to explain. It should have empirical reference. A hypothesis should be forward and future oriented. Next, it should be a pivot in scientific research. All research activities are designed for verification of hypothesis. Next, it should be adequate enough to explain the observed facts. Now, let us summarize the session. Science is a cumulative and endless series of empirical observations which results in the formation of concepts and theories, with both concepts and theories being subject to modification in the light of other empirical observations. Before we attend the next unit, please try to answer the following questions. Training in method is more important than the acquisition of fund of information. Comment. Distinguish between inductive and deductive method. What are the characteristics of scientific method? Now next, what are the basic steps involved in scientific method? And last, explain Mill's 5 canons of induction. Now we will see the references. Principles and Methods of Techniques of Teaching by J.C. Agarwal, published by Vikas Publishing House, New Delhi. Towards a Theory of Instruction by Bruner J.S. by Harvard University Press, Cambridge. Policies for Science Education by Fitzpatrick, published by Bureau of Publications, Teachers College, Columbia University, New York. Science Education, Theoretical Basis of Teaching and Pedagogic Analysis by Rainbow Publishers, written by Matthew T.K. and Molecule T.M. Hope you have enjoyed this session. We will meet in another session. Till then, bye.